Look at practice question set number 7. We start off in the information box. It says an experiment is performed using an initially neutral metal sphere and a positively charged dome of a Van de Graaff generator. Now, you guys probably wouldn't know anything about this, a Van de Graaff generator, a static ball. If we have time later today, we'll actually use one, if we have time today. If you did know something about it, you would know that the dome of the Van de Graaff generator is usually actually negatively charged, not positively charged. So that might be something, if we had used it already and I had told you about this, this might be something that you want to draw attention to, right? Okay, for you guys doing this over the weekend, that wouldn't have stuck out, right? Because you wouldn't have known the difference between it's supposed to be being positive or negative. Okay, but for me, that's something that I definitely want to draw attention to. A positively charged dome of a Van de Graaff generator. The metal sphere, which hangs on a thread, touches the dome of the Van de Graaff generator, then is repelled. The mass of the metal sphere is this. Says the diagram below illustrates a metal sphere in equilibrium. What does that word mean, equilibrium? What does that word mean? What does a word mean in any context? You've seen this before in other subjects as well. You've probably seen it in biology before. You've probably seen it in chemistry before. We've definitely seen it in physics 20 before. What does the word equilibrium mean? Yeah? Yes, balance, right? We see that in chemistry and biology, balance. It's not quite the same thing in physics, but more or less. When we talk about equilibrium in physics, we say it's balanced forces. Okay, so an object is either at rest and stays at rest because the force is balanced, or it's moving at a constant velocity and the forces are balanced. So whenever you see an object that is moving at a constant velocity or at rest and remaining at rest, then it is in a state of equilibrium, and it does mean that we have balanced forces here. Now, I don't think for the questions that we're going to see for this that actually matters. Okay, when this appeared on a diploma exam, there were more questions that went with this where the idea that it was in equilibrium did matter. It's just that they're not relevant to the topic that we're doing here. Now, the analysis doesn't actually affect us in solving this question today either, but just know that on this metal sphere, there are 3 forces. I don't like the way they have it drawn here. They have it drawn as a vector diagram. Okay, I prefer to draw it as a free body diagram where we have a force of gravity acting down. We have an electric force acting this way. Right, it must be, but it's pushed away from the Van de Graaff generator, and then we have a force of tension acting this way. All right, does that make sense? Again, we don't really need to do that to use that here today for the question that we have, but it's coming. Okay, you are going to see a few questions like this where you have to draw that free body diagram down the road. Here's the question. It says, when it touches the generator, the metal sphere becomes blank as a result of charged, positive or negative charge, as a result of the transfer of blank. Let's answer the second part first because I think that's easier. What transfers? Protons or electrons? Yeah, right? Always? Yes. It is going to be electrons always. So the answer is going to either be A or C. Now, does it become positive or negative? The Van de Graaff generator was positive. This is neutral. When positive touches neutral, what do they both become? Positive and positive. They want to balance out. Probably not going to balance out here, right? Can you tell me why they're probably not going to balance out here? They're going to try, but they're just probably not going to be successful here. Yeah? I'm sorry? Yes, their size is dramatically different, right? Typically, the bigger object can hold way more charge than the smaller object. So we like the idealized situation where we have equal size, equal shape, equal material. And then when we touch them together, say 0 and minus 10, they balance out to be minus 5 and minus 5. Whereas 0 and plus 10, plus 5 and plus 5. Here we're more likely to get something like 0 and plus 10 balance out to be 1 and 9 or something like that, right? But they're both going to be positive, right? Any way you look at it, they're both going to be positive. So when positive touches neutral, they end up being positive. When negative touches neutral, they end up being negative. The goal is to balance. Doesn't always happen, but they're always going to end up with the same charge. Okay? Now, notice it's a metal dome of a Van de Graaff generator. It's a metal sphere. The reason they're telling us that is because metal is a conductor, right? And we know that what we expect to happen is going to happen in conductors. If we touch two insulators together, you can get a charge transfer. You can. But how much transfers? Like, is it going to really make them both positive? Like, it's kind of iffy, right? By making them both conductors, we know what we expect to happen happens. Okay? All right, next question. Three identical conducting spheres again, so that when we touch them, what we expect to happen happens. 1, 2, and 3 have initial charges of +4, -2, and -4. What happens when they come into brief contact and then are separated? What is this whole thing, this thing right here? Yeah, good. It's microcoulombs, 10 to the -6 coulombs. Not that it really matters for us in this question, because there's no real calculation to do here, right? Other than average, which means the units don't matter. You guys remember what to do, right? Create our little table. 3 spheres, 1, 2, 3, and then let's create a 4th column for our total. Yep. This was the example we did in class, for it. If we had, it's just a situation where 1 touches 2 and nothing else happens, then we would add those up and divide by 2, correct? We'd average them, right? Well, we do have 1 touching 2, so we are going to add those up and divide by 2. But the only problem is we have other events taking place as well. 1 touches 2, then 2 touches 3, then 1 touches 3, like more than one event taking place. That's why I create this table to help me to kind of separate the events that are taking place. I'm going to start off by saying the charge of number 1 is +4 microcoulombs, -2 microcoulombs, and -4 microcoulombs. What's the total charge among all of those? 4, -2, -4 gives me -2 microcoulombs. Yes? The only reason I want to have that 4th column is as a check. It's a nice little check to make sure that I'm doing it right as I go. Now it says in step 1, 1 touches 2. So let's circle 1 and 2. Circle 1 and 2. And balance them out. Like, pretend the others doesn't exist right now, right? 1 touches 2. What are they going to balance it to be? 4 and -2 balances out to be what? Well, the total is 2, right? But we have to divide that by 2, right? 4 plus -2 divided by 2 is 1. So 1 becomes +1, 2 becomes +1. What happens to 3? Nothing. Stays the same. Nothing's changed, right? It was one event that just took place. Let's add these up. +1 + 1, -4 gives me, oh, look at that, -2. So again, that 4th column is just a little check for us, right? Odds are, if we had done this wrong, we would have gotten a different total charge. We know the total charge has to remain the same by the law of conservation of charge. Okay, what happens next? Step 2. 2 touches 3. 2 touches 3. Okay, 1 and -4. -3, divide that by 2 gives me -1.5. What about number 1? Still +1. Let's add these up. 1 plus -1.5 plus -1.5 gives me -2. Like, there's no guarantees that I've done this right when I get the same total charge, but odds are I have. And then step 3, 1 touches 3. 1 and -1.5 gives me -0.5. Divided by 2 gives me -0.25. What about the second one then? Stays the same, -1.5. Add them up, and we get -2. So if you do this, you have that 4th column where you check the total amount of charge, and you get the same charge all throughout. Should be, right? If you get the same charge all throughout, then odds are, I'd be like 95% confident that I've done this question correct. Okay, so we're looking for the total charge on sphere 1. I look at this and say, yeah, you know what, I'm pretty sure that it's -0.525 microcoulombs. And sure enough, that is the correct answer here. If you had forgotten to divide by 2, total charge wouldn't have worked out, right? And you would have known, you wouldn't know what your mistake was, but you would have known that you would have made a mistake. And the last question we have, the number of excess electrons that a ball has, it has a charge of negative 3.6. How do we find the number of oranges in a bag? Total mass by the, no, we want to find the number of oranges. So the total mass divided by the mass of 1. Here we're going to say the total charge, total coulombs, total charge divided by the charge of 1. Negative 3.6 times 10 to the minus 17 divided by negative 1.6 times 10 to the minus 19. And I think it gave me 225. 2.25 times 10 to the 2, which we'd express as 2252. If this was B times 10 to the W, we'd express it as 2.25, right? Most times in the newer questions, we see the A, B, C, D in the newer type questions, but you could see still B times 10 to the W. Okay, be ready for both.